In a double displacement reaction, you have two aqueous solutions mixed together, and two new compounds are produced as a result. Two reactants are ionic compounds dissolved in water, so their subscript is AQ. Basically, what happens when you have a double displacement reaction is the first part of the compounds in the reactant side switch positions and make two new compounds. So the cation A is now bonded to the anion B, and the cation A is now bonded to the anion D. Now you have to remember to pay attention to proper nomenclature. So we need to write proper formulas for our products. Solutions are homogeneous mixtures of solutes and solvents. A solute, by definition, is the substance that is dissolved, and it's always the substance that's there in the smallest amounts. If you get two substances that are in the same state, like two gases, it's always the substance that there's less of. The solvent is the substance that dissolves the solute. Solutes in double displacement reactions are ionic compounds, and the solvent is water. That's why they're AQ for aqua, water. Solubility is the measure of how much of the solute can dissolve in a known amount of solvent, like 100 milliliters of water or 1 liter of water. If a substance has a high solubility in water, that means it's very soluble, you can dissolve lots of it. It has a subscript of AQ. However, if it's not very soluble, it starts to precipitate out, so you start to see solid pieces floating in solution and coming down, and we would write that as a subscript S for solid. So precipitates, you write as an S for solid subscript. So we use solubility tables to determine whether the substance is soluble or not. And there's different ways to look at them, but this one has the negative ions, the anions, at the very top here. And on the side here, we're going to be dealing with cations and, as a result, solubility. So if you find your cation in this section of the table, we're going to be soluble, and our subscript will be AQ. If you find your cation in this lower part here, then it is a solid. It is low solubility, so it's not soluble. So cations, again, the positive part of your compound. If it's not soluble, low solubility, it's got an S subscript. And if it's at the top, it has high solubility, it will dissolve. So what you do is you find your compound, let's say sodium chloride. So the second part is the negative part, and that's your anion. And you look in the chart and you find out where that anion is. So you always look at the top. And this first column contains our anions. So what you do is then you look for your positive ion, your cation, in the table below it. So now we're going to look and see where sodium falls in the chloride column. So it says here most are soluble. All group 1 compounds, sodium's group 1, including acids, and all ammonium compounds are assumed to have high solubility in water. So sodium is a group 1 metal. It's an alkali metal, so it is categorized as high solubility with compounds. If you had low solubility, you would be one of these 6 down here. So sodium chloride then is found at the top. So its subscript will be AQ. It's highly soluble. Another example. Let's look at silver nitrate. Silver nitrate. So the anion is the second part. So look up here for nitrates. Here it is. It says all are soluble, none are solids. So the top half is your AQ, bottom half is your solids. No nitrates are solids in water. All of them will dissolve. So silver nitrate has an AQ subscript. Let's do another one. Let's do lead to chloride. So we are going to look for chloride again as our anion, and then we're going to look and see where do we find lead 2. Most are soluble. Is it one of these on the bottom? There's lead 2 plus. So it's on the bottom, so it's a solid. It does not dissolve. It precipitates out. Okay. A few more examples. Let's do magnesium hydroxide. All right. Like that. Magnesium hydroxide. So our negative ion, the second part of our compound, is hydroxide. So we come to this column. Group 1, ammonium, strontium, barium, and tellurium have high solubility, but underneath, most are not soluble. So if you're not at the top, you fall in with the most at the bottom. So magnesium is not at the top, so it must be in here with most. So it is solid. What about ammonium sulfate? The negative ion, the anion, is sulfate. Find sulfate. And ammonium is not on the bottom. It's not one of the solids, so it must fall in with the most. So this substance is AQ. It's soluble. You add the solid to the water and it just keeps dissolving. A double displacement reaction will only occur if one of 3 different things are seen. You get a precipitate. You actually see a solid forming. Don't forget that a precipitate is a solid. You might see that gas is produced. So you actually see bubbles in the liquid. So that means a gas is produced. And a change of pH happens. So if you have a neutralization reaction, if you've got an acid plus a base, you will make a salt plus water. So basically, this side has a pH of 7. So therefore, it is neutral. There's been a change of pH. If you were an acid, you had a low pH. If you were a base, you had a high pH. You mix them together, there's no pH, your pH of 7. All right, so these 3 things are clues that a double displacement reaction has occurred based on your observations. If the both products of your double displacement reactions are soluble, then we won't see a reaction, so we put NR for no reaction. You just end up with a beaker with a bunch of ions floating around. So, is calcium hydroxide soluble? Let's do some examples. Calcium hydroxide. CaOH2. Oh, why my brackets seem to look like C's. Okay, so we go back to the solubility table, look up hydroxide, see if calcium falls in to the solid or the AQ. So if we look at this chart, find hydroxide, here we go. At the top, there's no calcium, so it must be in the bottom with the most. So calcium hydroxide is a solid. All right. Now, complete this equation. Lead 2 nitrate plus potassium iodide makes what? So first thing you have to do is write out the chemical formulas for your actual products. So lead has a charge of 2 plus, iodine has a charge of 1 minus, so we need 2 of them. And then potassium nitrate. Potassium's got a charge of 1. Nitrate has a charge of -1, so that's correct. We are switching the front parts of both of these compounds. Okay, so now we have to figure out what their solubilities are. So we've got lead 2 iodide, so go to the halogens. Here's iodide. Most are soluble, but lead 2 is found in the bottom. So this compound is solid. And then potassium nitrate, we know from before that all nitrates are soluble, so KNO3 has a subscript AQ. And now all we have to do is balance this chemical equation, and then we're done. So we need 2 KIs, because we need 2 iodines. We need 2 iodines, we need 2 I's, which gives us 2 K's, so 2 potassiums. So we need a 2 over here. That gives us 2 potassiums now, but it also gives us 2 nitrates, and we have 2 nitrates, 1 lead, 1 lead. Voila, balance. Okay, we need to do 3 more examples. So, example number 3, complete this equation. We have iron 3 chloride plus sodium sulfate. What do they make? Well, we need to switch this first part again. So we put iron with sulfate and sodium with chlorine. So iron 3 sulfate. Sulfate has a charge of 2. So when we cross and drop, and iron has a charge of 3, there's our iron 3 sulfate formula, and sodium chloride. Okay, so we've got our solubility table out. So we need to find iron 3 sulfate. So sulfate is here. Iron 3 plus is not on the bottom. So that must mean this compound is AQ. And sodium chloride. We come over here to the chlorides. Sodium is up here with the most, so this is also AQ. So when you have a reaction that has two AQ products and nothing else, you don't even have to bother balancing after, because you put a line through it and it's an NR. It's a no reaction. What basically happens is, I'll move this up for a minute. You end up with, got our beaker of iron 3 chloride. And it's soluble. So it's all ions. It's not FeCl3 solid, it's AQ, which means it's actually ions. Then we have a beaker that is sodium sulfate, and sodium sulfate is soluble, so that beaker has sodium ions floating around and sulfate ions flying around. You mix them together in a bigger beaker. Because there's no reaction, we still just have these ions floating around. They're bumping into each other, but they're not doing anything. They're just hanging out, watching the world go by. They're spectators. Okay, let's get back to the fourth example. Okay, complete the following reaction. You've got HClAQ and LiOH, so hydrochloric acid and lithium hydroxide. We have to switch the front part of our reaction, so H goes with OH and Li goes with Cl. HOH can also be written as H2O, and that is a liquid. You do not form water AQ. Water dissolved in water does not exist. You form liquid water, and then the only part we have to look up in the solubility table then is lithium chloride. Come over here, and we have lithium up here with most, so this is AQ. So this is a case of a neutralization reaction. We have an acid, hydrochloric acid, and a base, lithium hydroxide. They will make a salt, in this case lithium chloride, and water, H2O. This is definitely a double displacement reaction. Even though you don't have a solid product, you have a change in pH, you have an acid and a base, and they make a salt and water. All right. Next question. Example number 5. Is the following a double displacement reaction? We have HNO3, so nitric acid, plus potassium carbonate, both AQ. We make carbon dioxide, water, and potassium nitrate. Sometimes you're going to do reactions, and this is, by the way, this is a double displacement reaction. But when you do this, you would have got K switching with H, so K, NO3, plus, so now H goes with CO3. CO3 is 2 negative, so we need 2 of them. So we would get potassium nitrate and H2CO3, hydrogen carbonate. So if we look at this, we're going to find potassium nitrate, of course, soluble, AQ, carbonate, group 1, and ammonium, or AQ. Everything else is solid, but hydrogen's group 1. So we would write AQ, AQ. So we would assume right off the bat that this was a case of no reaction, but it's not, because we form a gas. What happens is H2CO3 breaks down, it's carbonic acid, not hydrogen carbonate. It's carbonic acid, and it breaks down further into CO2 and H2O. So if you find you get an AQ product and H2CO3 AQ, you don't actually have that as a product. You react it further to get H2O, CO2, and your ionic compound. So this is a double displacement reaction.